Hello. Nice to meet you all, actually. Yeah, thank you for surviving till like this last talk. Yeah. So my name is Ilja. Yeah, I represent PySquared. I'm an engineer manager at PySquared. We're actually big friends with runtime verification. We kind of spin-off company. Actually, with the idea originated within runtime verification. Yeah, but yeah. So okay. So have you heard about like verifiable computing? So maybe are they in your okay, Raul? Yeah, but maybe anybody else? Okay. So the idea is pretty actually simple. So that's something that people call ZK in the crypto space, but originally like verifiable computing, yeah, has been invented like long ago. So it's a way actually how you can prove that some execution happened without or with actually, depending on your like problem statement, revealing some data actually about this execution. So the simplest example, for instance, if you have a program that generates some, I don't know, promo codes, and you wanna, I don't know, sell these promo codes for someone, but at the same time, actually, this person shouldn't show you this promo code. So just to avoid like the chance of cheating. So you can actually use this technology called verifiable computing. You can execute your program within some specific environment or write this program in a specific way and actually guarantee that, for instance, provide certificate that you generated this promo code by a specific program and you actually don't know the result of generating. So you don't know the promo code itself. For instance, it was sent to your email or something. But originally, the current state of art is actually so there are many flaws in the current state of art how people do verifiable computing, especially in the crypto space. So the problem is that, so like, do verifiable computing for existing computations, it's really expensive because we have quite complicated programming languages. We have EVM, we have Rust. So to actually generate zero-knowledge proofs, for instance, using existing infrastructure, you need to trust different software, quite complicated software, actually millions of lines of code. So you need to trust specific circuits designed for this purpose. You need to trust interpreters or compilers. So actually, yeah, it's not the error-prone way. So even if on paper it could look like really like Grail, but in practice, it's really difficult to achieve real like safety. So because no one actually would generate like, I don't know, do some formal verification of your infrastructure, because actually it's quite complicated and big. So what PySquared brings to the space is a completely different way of thinking. So what we do is actually, we kind of provide a way how you can do some integrity checking of what verifiable computing does actually. So imagine a analogy with TCP/IP. So for instance, I don't know, you want to send a message from Alice to Bob, and what you need to do is actually to have some guarantees that, for instance, you use this like TCP/IP protocol, the message will be like actually arriving Bob without any changes, right? So you have like this tag, and you don't care about like this messaging in the internet. You know that actually it will be delivered, delivered without changes. So we don't have in the current like I know state of art for verifiable computing. So what PySquared actually does, we bring like this level of like trust to the space. So we introduce additional artifact called like mathematical proofs actually into the game, and using like a proof checker for this mathematical proof, we can guarantee actually that verifiable computing happening according to actually our intentions. So once I attended Microsoft Research Summer School back, and there was a good actually talk about like revolution in different tech areas. So and the question was like how you can even come up with something, I don't know, genius. So they actually told us that we were like PhD students. They told us that there are actually two ways. One is very difficult, and it's really just happens by chance when you can come up with some brilliant idea. But usually what people do, they combine some cool actually ingredients already existing in the text space, and actually a result of this combination brings you to something brilliant in the space. So that's what we are trying to achieve in the PySquared. So we have 3 K ingredients actually. First one is also actually called K framework. We have matching logic and zero knowledge certificates. So these all like 3 items already exist, so we don't bring anything like crazy new, but we actually came up with a super cool actually way how to compose them to achieve our final goal. So let me start with the K first. So the K is executable semantics framework. It's been years like when it was announced and released, so there are many scientific papers. It's already actually battle tested and it's applied by runtime verification in different commercial engagements. So it's the thing that actually allows you to generate mathematical proofs in our problem statement. The idea is pretty simple. You can define language semantics and actually by defining the language semantics, you can get automatically different kind of tools. You can do symbolic execution, you can do didactic verification, you can have parser, interpreter, compilers, like other tools. So the good thing about like language semantics is that it's pretty easy to define and test. So in traditional like programming languages way how to like define programming languages, what you need is actually to define, I don't know, interpreter or develop a compiler or something. So the things how the programming language is, what actually does it do? So they're hidden inside of like this complicated software. In the semantics framework, they are all explicit. You just need to write specific program called like this language semantics that just explains step by step what each statement in the program, what each operator or something actually does in the program. For instance, how the so-called like program state is changed by certain kind of like operation in the programming language. So you can actually even test it using K, using existing tests already developed for existing compilers or anything. So another step, another thing actually that we use in our product is mathematical proof. So mathematical proof is just an artifact generated for some specific claim. So if we speak about the K, so K requires this language semantics plugged in as an input. Oh, sorry, haven't. Does it work? Okay. Yeah, so, and as input, you actually can provide not just the program, but you also can provide some additional requirements about this program execution. Imagine you, for instance, you're sending some ETH, I don't know, from Alice to Bob, and you want to ensure that balance of Bob will be definitely increased. It couldn't be, I don't know, go below the previous like value. So to ensure that, you can like write some kind of specification added to the program. So we call it claim. But actually, claim can be empty, so you can have only your program. So you can feed it to the K and get so-called like matching logic proof. So what's the proof like by itself? What's nature? So the proof is specific, actually theorem. So it's just written in a specific formally defined language. So in logics, we have so-called like model logic. So it's kind of model logic. It's defined using separate like logical constraints, constructs, that has a limited set of simple proof rules. So the matching logic itself has been developed already by more than 15 years. There are many like peer-reviewed research about that. But what's important about the matching logic, it's kind of specific mathematical logic that allows to capture execution of almost any or maybe any programming language. So that's important. And the proof itself, it's just like simple sequence of some axioms, like initial statements that we trust. In this example, it's a statement that, for instance, I don't know, if it's raining, then I will get wet. And we can have another axiom, for instance, it's raining. We have also some claims, something that we want to prove. For instance, this is the latest statement, I will get wet. And we have proof rules. The proof rules are specific rules in logic that we can apply to actually deduce this statement. So we just say, for instance, if we have like modus ponens logical proof rule. So we can simply deduce this like the result from these two statements. So I don't go in too complicated details. So the final part is zero knowledge proof. So why do we need zero knowledge proof? So zero knowledge proof just work as a compression tool. So matching logic proofs are pretty big, so we can generate them as a stream. But anyway, so like the result of executing the program, like and explaining all steps of the program in as actually mathematical formulas could be quite big. So that's why actually we need some compression tool. And actually to just avoid compressing it per se, what we do is actually we just run a specific program called proof checker. It's pretty simple. It's just like the simplest implementation that we have right now. It's just 200 lines of code. What it does, it just checks the consistency of the generated logical proof. So what we need to do is actually just to check that actually logical proof, it's correct from the perspective that it applied only like so-called like valid proof rules. It used axioms that have been there like as our trust base, that like there is no like, I don't know, kind of facts introduced during the proof rule itself. So everything like is connected and makes sense. So this small program actually could be executed in some ZK environment, existing environment, and we can, after like running this program, generate a ZK proof that actually shows that not just the proof was correct, but actually execution was correct, because we got this execution actually from, actually we first like generate mathematical proof for the execution, and then we got like the ZK certificate. So ZK certificate actually valid for the execution. So this is the final, like the main actually idea. So how we combine our tools to actually do a lot of different things in the space. So again, just to go through all like these components in the picture. So we have some programs, initial programs. They can be written in any programming language. If you have your like programming language semantics defined, for instance, we have like KVM, we have KWASM already defined and supported by the runtime verification. So we can generate actually mathematical proofs using K. What we can do next is that we can actually run this simple programs called like proof checker inside some ZK environment and get actually zero knowledge proofs for that. So it's much simpler way how things work right now, because simply we can plug in new programming languages really seamlessly. We don't need to invent new circuits, new actually zero knowledge environments for that. So we can actually do many things here. So for instance, we can summarize proofs and generate not just, I don't know, mathematical proofs for the program itself. We can generate summaries actually for execution of some programs, like compressing them using like K. We can also generate, for instance, check marks that some smart contracts have been verified by actually running formal verification tools and actually with the support of our environment. For instance, right now, if a company like, I don't know, carries out some formal verification and they got this like check mark on their side, you can't actually verify, right? So that they actually have verified the recent version of the software that they actually provide or they support. But using like this kind of pipeline, you always can do some kind of checking. You can have for formal verification also some kind of guarantees, some certificates that people can verify by simply running, I don't know, ZK checker or something. So there are many actually use cases in the area that can be implemented using our tech, so called actually proof of proof. So, but what we started doing recently is building a product called Universal Settlement Layer. So Universal Settlement Layer is a component in the model blockchain space, actually. So it sits between the execution layer and above consensus or DA layer. So what it allows actually to do is to eliminate the need for messaging platforms and actually simplify bridging for cross-chain applications. So it allows to expose actually trust, because actually what we can do is reduce trust base for actually modern quite complicated infrastructure. So we'll talk about it slightly later. And also we can do is actually mitigate fragmentation between like 4 applications that would like to use different DA layers. So again, just to emphasize, so why actually does proof of proof look like as something that actually brings some more innovation in the space? So again, so secret sauce first is universality. So as I mentioned, so K uses language semantics. So you don't need actually to rewrite anymore your compiler or interpreter when you need to introduce some changes in the programming language. So what you need to do is actually just to change your language semantics, carry out some testing, and that's all actually. You don't need to change the underlying infrastructure. You don't need to update your even ZK circuit. You don't need to update your ZK VM. It's really simple and easy to prototype. So if you're going to build your own, I don't know, solution or programming language and you want to quickly build a ZK rollup, you don't need to think about how to like build all like this complicated stuff. So another thing is trustless. So the core thing in trust is actually trust-based in the space. So for instance, if we consider current like state in the traditional space, like traditional finance, so you need to trust a lot of actors that you don't see. For instance, when you buy a cup of tea or a cup of coffee, you actually pay with the card and you interact with different players. So acquirer, card association, issuing bank. So you have some actually trust base. So you need to trust acquirer, you need to trust card association, you need to trust actually maybe issuing bank, you need to trust this point of sale. Merchant as well also has its own trust base. It needs to trust actually merchant bank and other like components. So the same actually about this like trust base in DeFi. So there are many data sources that you need to trust actually doing your transaction. You need to trust data sources. You need to trust, for instance, oracles. You need to trust some smart contract you are interacting with. You need to trust, I don't know, wallet implementation, ETH node, and actually compiler sitting inside the node. I mean, not the compiler, but yeah, virtual machine. Yeah, but anyway, so there are a lot of things that you need to trust. And if actually we're moving towards like this new area of modular blockchain, it's getting worse, right? Because actually there are many like this modular blockchain components. It's not anymore like central, like, I don't know, component, and you want to actually see what's happening, right? So if you interact with different products, with different like these layers, you want to actually see what you need to actually to trust before you, I don't know, send your like, I don't know, money inside this system. So what we actually want to do is actually expose this trust, show this components, these actors actually in like exactly in like transaction metadata. And what we can do actually eliminate some certain players here. So we can reduce the trust base by using our proof of proof technology by actually reducing to 2 main actually players. So speaking about like interpreters, for instance, if you have a language semantics, if you have this proof checker, you don't need to trust actually virtual machine anymore. You don't need to care about like vulnerabilities sitting in the compiler, because this is actually could be easily first like spotted by the K actually executing your transaction, and also while the mathematical proof is generated. So now it doesn't like so there is no any danger is in, for instance, that there is some bug in K, because if the proof generated incorrectly, it would be easily spotted by the proof checker. So you need only to trust your language semantics, explicitly defined, actually written. You can send it to your, I don't know, friends. It can be easily audited. It's human readable. It's executable. You can even test it with the K. You can, and yeah, the second thing you need to trust is this small proof checker. It's scalable, really small, 200 lines of code, and formally designed. Okay, and the last component is scalability. So first, like before I like talk about this point, so I want to just show you that. Okay, maybe it doesn't make sense. Okay, I want to just like emphasize that logical proofs aren't the programs itself. So they are completely stateless. So the proof itself is just a set of lemmas, so-called, like, I don't know, theories. You can consider them as theories, and each theory has its own proof. So you can actually prove all like these theories completely independently. You needn't actually care about like what's happening after a certain theory. You just need to like do checking all like this like theorem proofs in parallel, and then just double check that all like claims they form a valid actually chain of claims. For instance, that if we start like proving a theorem or claim with certain assumption, this assumption has been sitting as a claim or different theorem in the proof, or it was a part of the initial like trust assumptions. So that's why actually scalability is one of our strong point. Oh, sorry, it's different. Strong sides. Yeah, so we have implemented our proof checker using different programming languages. So we already have a prototype working in RISC-0, ZKLLVM, LORC, yeah, Cairo1, Cairo0. So there are many things we can approve actually. So it's just numbers actually that we obtained at the end of the last year. So we switched to development actually our own circuit using Circom, mostly because we want to like make it more fast, more scalable, get more control over actually cryptographic operations. Because the thing is that in the logical world, we have many operations that could be actually carried out much more efficiently than in existing actually ZKVMs. So that's why we consider in development our own solution. And yeah, so our current vision on the USL architecture, it's also temporary, so because we actually just recently embarked in our journey. So the idea is that it will be a chain, or that would be actually that would contain different blocks having transaction in different programming languages. So you can easily actually using our tech support execution for different kind of programs, for instance, even generated by different execution layers, like for different rollups coming to us, we can sequence them and combine them together. Actually, for instance, if you want to like build some, I don't know, breach or do some different actions on different chain, you can even like in the same block or in the same transaction verify that, for instance, one transaction in EVM does something like step A, and then there is another like transaction corresponding to the action intended for different like I don't know, smart contract written in Rust in a different ecosystem that you actually can connect together. So the thing is that we only need to settle this mathematical proofs. We need only to support mathematical proofs. All right, so yeah, join our efforts. So as I mentioned, we just like recently started. So we have our tech in place. If you have any great actually ideas how we can cooperate and help each other, so yeah, feel free to reach us, and yeah, let's do verifiable computing together. So thank you.
Can we get one applause? Do any of you have any questions? It's a large audience, so someone has to have one. Thank you. Give me something to do here.
Yeah, so my question is about how easy to like write these all these things for for developers, so to generate the proof, because it looks like sometimes like developers like even lazy to write the tests and here they need like it looks like they learn like new framework and like do you have any ideas how to make it simpler or something?
Yeah, the idea is actually we don't need people to write their own frameworks. We don't need them to support new programming languages. That's something that we want to actually carry out themselves, or maybe outsource to existing companies, such as runtime verification, which are actually great in development, language semantics. What we want to do is actually get like this language semantics ready in place. We will support more of them. So first steps likely will be support EVM, because we already have KVM, and support WASM actually, because we have some prototype for the KVM WASM semantics. So And that's all actually. So for instance, to generate ZK proof, you don't need anything. So proof checker is developed by us. So K is developed by us. Yeah, you don't need anything actually. You can just like take our tech and give us your program, and we will generate proof for you. But the thing is that on the like universal settlement layer, so we likely considering like B2B customers. So maybe we will talk more about during the next events about how actually we plan of like and helping people to integrate and build on top of the USL. But it's not like main topic of my talk today.
Okay, thank you. Well, so for that, first you need to cover everything by formal verification to generate the proofs, right? And
yeah, so but formal verification, it's in place. The problem in formal verification is that it's difficult to prove something that actually kind of doesn't sit inside the program. So if there is like separate claim about the program, it's difficult actually to go through the program right and prove that. But in our case, what we do actually, we just follow line by line through the program, like generating this mathematical proof. And the only thing we need to do is actually just to check it consistency. So in our like practical evaluation, we can generate proofs really fast comparing like with existing solutions. So the last comparison was for Geth. So Geth, like only part like actually like that executed like EVM code. It works, faster, but maybe 2-3 times faster for certain benchmarks, not like 10 times slower. It's really comparable to like cutting edge solutions right now.
Does that answer your question? Okay, can we get one more applause for Ilya? Great talk.
Thank you.